We should be rolling. We should be rolling. Okay, we're rolling. Um, so Welcome back to Create Labs. This is part two of the stream of building RAG in Pure C. I'm your host for today. I'm Thrilla 3 again. Make sure to check out the first part if you want to follow along. I don't think anybody will follow this, but yeah, we're just doing it for learning purposes. So thank you for joining in. We are gonna start streaming right now, and I hope this will be a long stream. So yeah, sit back, relax, all that stuff. All right. Okay, let's start. Yesterday we left off at a point where we were doing yeah, we did not write any code as of now. We just wrote a header file like this. So we defined a chunk h header file, and we defined two public APIs which the caller can use. So chunk text is one. So this first function is just for returning an array of chunks uh, when you input const char pointer to text. So when you input a string, the actual document string, and you define a chunk size, you define the overlap between the chunks, so that again we discussed that overlap is used for between two chunks when we want a kind of an overlap between the two chunks, so that we get a better answer between the two chunks, so that we do not miss on any information that is available, that might not be available in the first chunk but might be available in the second chunk. So that's the idea behind overlap. And wait 1 second, I'm not too sure why overlap is there in this function. um, yeah, okay, yeah, it should be there because we're defining the overlap there. And int num chunks is the number of chunks that should be made from the text, right? Okay, and this is the other API that we are using, which is chunk free. So after you in this function, we basically malloc the number of chunks into an array of strings, and the next function is about freeing the chunks so that the caller can just make a handler, sorry, help. It's just essentially a helper that the caller can call, and you can free the chunks into memory, and ending it with endif. So that's what we wrote yesterday. Okay, which was not much, but yes, with a start. So yeah, so we'll go through logic, and we stop again for writing the implementation. So I asked Claude to go through the logic step by step. Checking, okay. Is it stuck? It is stuck. Let me do it again. Let me do it again. even know this thing? Okay, it should work. Okay, it is working. Alright, so again, yeah, I don't know if you have missed the code again. Let's just go with the code again. So this is just the code, basic public APIs that we're using. Chunk text and chunk free. So we're doing malloc for chunks, malloc for the string of chunks, and then we're doing this API call is just for the freeing of chunks after malloc it here. So the caller can use both. so so we'll walk through the logic step by step and before touching any code. Perfect. Let's think through it. So we're writing the implementation right now. So what chunk text needs to do? You give it a document like this, simplified. So, okay, with chunk size is 20 and overlap is 5. It needs to return an array of strings, each is most 20 characters, where consecutive chunks share 5 characters of overlap. It makes sense. It needs to return an array of strings, each at most 20 characters, correct? Where consecutive chunks share 5 characters of overlap, correct? How many chunks will be there? Before allocating anything, we need to know how many chunks the text will produce. Otherwise, we don't know how big to make the car pointer. Exactly. So, how many chunks will there be? So, depending on the number of chunks, we will divide the text into those many number of chunks, and each chunk being that much size. About chunk size and text length is the total length of text. Chunk size overlap. The step between chunk starts and chunk size minus overlap. Step between chunk starts is the step between chunk starts is chunk size minus overlap. Yeah, okay, correct. So chunk starts are at positions 0, chunk size minus overlap, 2 into chunk size minus overlap until we pass text length. Okay, so yeah, so the step should be exactly, so it should be chunk size minus overlap, because each chunk is chunk size, and so starting at 0 we'll go to chunk size but minus overlap. The overlap is not part of the chunk, is it? Yeah, seems like no, it is part of the chunks, but it's part of both of the chunks. So for example, if we think about it, the next chunk will start at chunk size minus overlap. uh yeah, let's make it clear. Why chunk size minus overlap? Okay, he sets at 430. Okay, that's fine. So let's use a concrete example. So your text is 40 characters, chunk size is 20, overlap is 5. Without overlap, chunks would start at chunk 0. Yeah, correct. The step between starts is exactly chunk size is 20. Clean cut, no sharing. Now with overlap, you want chunk 1 to repeat the last 5 characters. Oh, okay, that's the overlap. Okay, I thought the overlap is disjoint, so that's why I got confused. So it makes sense that overlap should be, if the overlap is shared, then the characters between the last 5 characters of the chunk 1 and the next 5 characters of chunk 2 should be the same. So essentially it is shared. Your chunk would not repeat the last 5 characters of chunk 0. Correct. Okay, that makes sense. Characters 0 to 19. Chunk 1 position 15. Characters 15 to 34. Yeah, starts 5 characters earlier. Okay. Okay, makes sense. So visually, it's just text chunk 0, and that's the overlap. Chunk size minus the overlap. Okay, so it's region between both chunks shared. Okay, that's cool. Guarantee that the region is repeated. Yes, okay. So that okay. Yeah, okay, it's happening. So overlap is the region between chunks, both chunks shared. By each adding the next chunk overlap characters earlier, you guarantee that region is repeated. Does that make the form messed up? Visible chunk size minus overlap clear? Yes. Okay. Makes sense. Okay. Okay. Let's continue. How many chunks? Yeah, given that we know step is chunk size minus overlap. Yeah, so number of chunks will be dependent on the text length. So the total text length um, number of chunks will be so text length is 40 if you say. Hmm. So for each step you knew that, but for the last element the overlap is counted again. uh, so sleepy, bro. The hell? 1 second. Okay, we're back again. All right. So step 2, how many chunks? So now that we know step 1 is chunk size minus OLAP, we can figure out the count. So text length is the total characters in the document. Step is equal to chunk size minus overlap. That's good. Number of chunks is equal to text length minus overlap by step plus 1. So step will be 15, right? Yeah, okay, step will be 15. So 40 minus 5, 35, 15 plus 1. These division C truncates for the text doesn't divide evenly. Yeah. So the last time might be shorter than chunk size, and that's fine. We just copy whatever's left. True. Yeah. So before moving to step 3, actually allocating and copying, one question. What do you think should happen if the user passes bad parameters like overlap is greater than or equal to chunk size? Step would be 0 or negative infinite loop. Text is null should be set return null or something else. Okay. So overlap if it is greater than chunk size or text is null, chunk size is 0. We should, I think, we should flag it. We should flag it. And return null, right? Yeah, we should flag it and return null, right? When I say when pure C, there's no exception system, so flagging error means choosing a convention. So return null imprint to S3, chunk size overlap must be less than chunk size. Yeah, I mean that's fine, option A, but return null silently call checks. So look at how I just handle this is etc. The function name is preview, then returns null. Clear minimal no errors. The always checks if the return value is null before using it. So yeah, so Antis basically does if the file border is null, whatever the file is open, and he prints out your str and returns null. I mean that's what we also want to do, right? Yeah. So yeah, that's that's option A is correct. I mean, silent return null, I don't think it's that good. So just print it out to str, then that's better, Good. So our error handling pattern will be if text. Yeah, exactly. So I'm just printing out to str. That's cool. So again, so we have if the text is null, then we print out to str that the text is null, or if the chunk size is 0, again chunk size cannot be 0 because there'll be an number of chunks will be infinite. Sorry, chunk size minus overlap, right? Yeah, so it will be infinite. or negative, which cannot happen, cannot be 0. And overlap is greater than chunk size. Overlap must be less than chunk size, obviously. 3 guards at the top of the function before any logic runs. Cool, that's nice. Allocating memory. Once we have validated inputs, we need to allocate two things. Okay, the char pointer array, an array of pointers, one per chunk, each individual chunk string. So char pointer array is the char double point array is a strong array of pointers, one per chunk. Okay, each individual chunk string, and malloc copy of the text slice. Yeah. Calculate num chunks. Yes, malloc the cap pointer array, num chunks pointer. Malloc the char pointer array. For each chunk, calculate the start position. Yes, for each chunk, calculate start position, calculate length, min of chunk size or remaining text. Calculate length, min of chunk size or remaining text. That is true. Malloc a string of that length plus one for. Okay, that's cool. Copy the text slice into it. Yeah, null terminate. Yes, it makes sense. That's really understand why we need the plus one for the null terminate. Yes, yes, we can do. Yes, yes. Um, yeah. Okay, let's look at step 3b. More carefully calculate length of each chunk. For most chunks, the length is just chunk size, but the last chunk is special. The remaining text might be shorter than chunk size, so the length is in start is group. I need to step, yeah. Int length is equal to chunk size. Yes. So if start plus length is greater than text length, length is equal to text length minus start. So yeah, okay. So start, that's the start of the last chunk, plus length, which is the chunk size. So going back to the last bit, and if it is greater than text length, then length. So yeah, so if it is yeah greater than that text length, then length is equal to text length minus start, which makes sense, right? Yeah, so in C, this game, we do write this using a macro that already exists in string.h. We said no dependence before beyond that's what's needed. Yes, so we write it ourselves this pattern. If A is greater than B, A is equal to B. Yeah, so if A is greater than B, A is equal to B. Okay, this is what the standard main would do, but in C main is not in the standard library for integers, so we just write the if directly. Before we move to actually writing to let's summarize complete logic we agreed on. Yeah, so validate inputs null chunk size is 0, overlap is greater than chunk size. Print out to print out to SDR, sorry, SD error, standard error plus null, and also return null. Yes, calculate text length. Yes, so and then step, and then number of chunks. Malloc the array of strings of size num chunks. Yes, loop I is equal to 0 to number of chunks minus 1. Okay, and then start is equal to I into step. Yes, length is equal to min of chunk size. So you're basically marking the pointers here, marking the pointers to the individual arrays, individual strings or individual chunks. And then into the loop we're doing 0 to num chunks minus 1. Start is equal to I into step. Length is equal to min of chunk size. Yeah, so again minimum is minimum of chunk size if it is there, or text length minus 1, and then again text length is the total text length, right? So and whichever is minimum, you just put it there. If the chunk size is minimum, that's cool. But if the text length minus start is lesser than chunk size, which only should happen when um, I mean, yeah, when it's the last chunk, and then malloc chunk string of length plus one. Yes, okay, yes, and then mem copy the text slice into it. Okay, yes, and I'll terminate it. Yes, and store in an array. Yes, so set pointer to num chunks. Yes, return array. Does it feel complete and clear? Yes, yes, we can do it. Uh, what includes the chunk.c needed? It needs for printf parameter. That's it. No external dependencies. Pure C and library only. So don't need SDIO, SDLib, SDIO for fprintf, which obviously we need SDIO for the interacting with the error messages and whatever input and output. So that's needed. Standard lib for malloc and free. Yes, we're not writing our own malloc and free. But there's yeah, maybe in another stream we can write, but yeah, not today. And then string.h for calculating the string length. mmcpy, that's cool. memcopy, right? Okay, chunk.h, its own header. That's it. Now let's install it. Yes, we can do it. Yes, we can do it. Chunk text and chunk free. Cool. Then we we'll just can see the code after it has written what the code is about. Okay, now you can see what it has written. So this is our first implementation of chunk.c. So it's about 52 lines. Okay, so include stdio. Okay, that's standard. stdlib for fprintf. Sorry, fprintf for stdio. stdlib is used for malloc and free. Yeah, and string.h for memcpy and string length. Okay, include chunk.h. Okay, cool. So we can see this API, the public API we're writing, car pointer chunk size, chunk text. We are basically returning the array of strings of chunks. That's cool. Based on we're taking the user's input for text, and we're doing const because we don't want to change the text itself, and it should be not changed throughout the file, so we're doing const. That is cool. And in chunk size to determine the number of chunks, and the chunk size depending on the chunk size, right? So in pointer num chunks, so we can return as a pointer, and the caller can actually use the num chunks to basically free it again. So again, if you see chunk.h, we're again passing in the number of chunks again here. So it's the number of chunks is needed to just free that many chunks. So that makes sense. So okay, validate input. If the again, so these are the just validating inputs. So if the text is null, we basically just do fprintf to standard error, check text is null, and return null. That's okay. And if chunk size is 0, we again print it out to standard error, chunk text is equal to chunk size cannot be 0. Okay, that's cool. And then overlap is equal to overlap is greater than or equal to chunk size. Chunk text is equal I mean it is the overlap must be less than chunk size. Yes, again that's true. And we're defining some variables to basically chunk it out. So in text length is equal to str length text. That's the actual text length of the whatever text the user has input, not the user, the document that we are looking at. And int step is equal to chunk size minus overlap, and that makes sense. Int step is equal to chunk size minus overlap. Yes, the as we discussed, the overlap is the shared area between the two chunks. So the start of the next chunk will actually be chunk size minus overlap. That makes sense. Yes. So int count is equal to text length minus overlap by step 1 plus 1. We can try to understand like how many number of chunks are there. Basically saying the count of chunks. I think you can understand it because so there's a text length. I don't have a pen, that's why I'm not writing it anywhere, but I'm trying to visualize it. Uh, so this is the text length, so it's like ABCD whatever, and chunk size is 1. So for example, that's 1, and okay, A B C D F and A B C D E F. Okay, if the chunk size is 2, so A B B uh that makes sense. So allocate array of chunk pointers, pointer chunks is good to malloc. So yeah, we're allocating the array of chunk pointers here. So malloc of count into size of pointer. Yes, okay, that is cool. The number of chunks depends on the count. So we're basically allocating um, those many number of pointers, array pointers, based on the size of a pointer, which is almost always 8 bytes. Sorry, 8 bits, and into count. So those many things. So that's cool. Array of chunk pointers. That's cool. And if the chunk if this if we have failed to get a array of chunks, the malloc is failed, then we just print it out to str chunks text is equal to out of memory. That's cool. For int I is equal to 0 and less than count I plus plus. Now basically we're starting to chunk it out and allocating to each pointer to the array of chunks, right? So each element of the array. Int start is equal to I into step, int length is equal to chunk size. Okay, the start the chunk will be always I into step. So yeah, step is kind of a nice variable that you can just use to step over. And int length is equal to chunk size. Cool. Int length len is equal to chunk size. Why is int length is equal to chunk size? Okay, we'll see. If start plus length is greater than text length, len is equal to text length minus start. Yeah, in length. So this is the length of the chunk that we are using, and then we can just do malloc, right? So yeah, we can just do malloc here. Chunks of I is equal to malloc of length plus 1. Yeah, length plus 1. Again, we're just doing it. We're just mallocing that those many bytes, which is the chunk size number of bytes, plus 1 uh, for the last byte, for the last null terminating element. Okay, if chunks of I, if it has failed, then we write it out to str error, and chunk test to get out of memory. That's cool. Free what we already allocated. For int j is equal to 0, j is less than I, and j plus plus free chunks of j. That makes sense. Free what we already allocated. Yeah, okay. That makes sense. Free of chunks. Free what we already allocated. Okay, why we freeing this? Free what we already allocated. So why we freeing that? Okay, I don't know. We're just basically going backwards. J is less than I. G plus plus till whatever we have done. Free of chunks. So we cannot. I think we're freeing it because so that we do not overlap Saturday, but that is just the job of Malik, right? So I don't know what this means. Think about it. So again, memcpy chunks of I. Taking in the text. Again, text is that text plus start, right? Okay, that makes sense. And we're just basically copying the length from the text plus start starting point, and we're basically copying length number of bytes to chunks of I. That is cool. And chunks of I of length is null pointer, so sorry, null terminating string, so to make it as a string. That is cool. And then we're basically again count is going to point to non chunks and the return chunks. Okay, that's cool. I think yeah, return chunks is basically again this the array of char pointers. Yeah, array of pointers to the chunks, and then we're returning that. That makes sense. Sorry, that makes sense. Therefore we can go again. So why yeah, so before moving to chunk free, we notice one thing in the error handling inside the loop. Yes, exactly why we're freeing it. If malloc fails halfway through, say on chunk 3 of 10, we can just return null and leak the first 3 chunks. Oh, okay. Oh, okay. So we free everything allocated so far, then free the array itself, then return null. Okay. Oh, okay, so we free everything allocated so far and then free the array itself, then return null. There's a common C pattern called cleanup upon partial failure. You'll see throughout the gte.c with go to error pattern. One question before writing chunk free. Do you understand why chunk free needs both the array chunks and the count number of chunks? Why can't I just take the array alone? Why chunk free needs both the array chunks and the count? Yeah, I think we like um only through num chunks we can free those many number of chunks by just going through the step, right? uh, or else we'll just free out which is free out memory that is not allocated so far. So I think num chunks is important. Obviously if we do not pass in the count number of chunks, we will free out. I mean, we won't. The caller won't know how many chunks to free, and we might accidentally free out memory that is not allocated, right? So I think that's the reason. So free chunks of J. So again, I want to understand like again. So let's just go through the code again, okay? Free. Yeah. So free what we allocated so far. So okay. So okay. This is in the if condition where malloc fails partially. Okay, that's cool. That makes sense. 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 We're passing in num chunks to chunk free so that the caller does not have to wonder about the number of chunks to free, and so that the caller does not accidentally free out non-allocated memory, right? Exactly right. Okay, that makes me feel good about myself. Even more fundamental reason in C, when you receive car point and pointer, you have no way knowing how many pointers are in it. Yes, obviously. The array is just a memory address. There's no length attached to it. See, it doesn't track that. Obviously, dog. I mean, that's what I meant, bro. Come on now. But I have no idea when to stop. Okay, but I should have told you that. Correct. How many times do we loop? We don't know. True. This is one of the fundamental differences between C and high level languages. Python at least knows its own length. C and array is just a pointer. It knows nothing about itself. Num chunks is the only source of truth. But how many strings in the array? That's good. Yeah, sure. Write chunk free now and add it to chunks. Yes. Let's go slow. I think chunk free is kind of simple, right? Chunk free. Let's try to guess what chunk free should be. Yeah, chunk free again. So if you think about chunk free, chunk.h. Okay, look at it. So void chunk free will basically just freeing out the pointers. We should actually free out whatever we did in chunk text where the malloc has filled partially here. Sorry, whatever we've done here, it's basically the same thing in chunk free, right? It's basically the same thing. So int number of chunks again, that's the thing again. Yes. So I think that's the reason, right? So whatever we're doing here, just paste it to that. That's right. So we can just yeah, write it, instruct it to write it. What's it now working? Okay, yeah, write it. Okay, and we'll define some of the things. Exactly. So just free the actual content of the chunks, and then again free the pointer to the array of pointers. That's all. Makes sense. Free individual string first, chunks of 5, then free the array pointers. If you did it the other way, free chunks first, you'll lose the pointers to the individual chunks and leak all of them. Obviously, strings.c are complete. Before we move to the next one, do you want to talk through what we just built, or are you comfortable and ready to move on? I'm comfortable. Let me just actually did not do git init here. Okay, so okay, there's nothing here. What? Okay, cool. Hard and typing, but okay. So we can just add -u git commit. Sorry, git add cloud MD. Yeah, we can add everything. True, and then git commit. Okay, we can just add. Sorry, let's just do init chunk.h chunk.c. Actually, 1 second. So init decisions.md, plan.md, chunk.c, and chunk.h. actually actually don't add claude.md, right? That's just for our use case, right? um, okay. How do you not reset dog? I don't get commands, bro. Okay, okay. Git add. Can you do this? Okay, no. How do you can do it? Let's get to move thing. Fine. Okay. I've been so spoiled that there is no need for me to actually commit by my own. So that's why this problem. Okay. Yeah, that's all. Okay. Okay, cool. Okay, cool. So we can go back. That makes sense. Um, that makes sense. Okay, I am comfortable. Let's move forward. But actually, like, 1 second. Let's just go through code again. Have we defined chunk size? No, not defined chunk size, but okay. That's on main.c. That's fine. Sorry. Okay. All right. Just checking if it's all right. Okay. Cool. It is happening. So again, let's see the code again here. For again this number of count, number of chunk number of chunks. Start is equal to I into step the start where you start the chunk, and then length is equal to chunk size. This is just the for the last chunk. That's cool. If chunks and malloc, and then malloc is length is 1, and then basically that's cool. And again, length is actually chunk size. Chunk size is actually so chunk size. Yeah, chunk size is that chunk size minus all of step. All right. And again, length is just chunk size. Okay, length is chunk size, not chunk size minus overlap. Yes, okay, got it. But step is actually chunk size minus chunk size minus overlap. So since step is chunk size minus overlap, um, and we're doing, I can just write it here. Chunk size maybe are basically copying the length from text plus start, and start is yeah, start is governed by step, and so there is a guaranteed overlap of overlap size between two chunks. I think that makes sense, right? Let's ask Claude. No? Yes, exactly. Cool. Cool, now I get it. Let's trace through it with numbers to make it concrete. Yes, chunk size is 20, overlap is 5, step is 15. Yeah. Chunk 0, start is 0, 15. So yeah. True. Chunk 0 ends at 19. Chunk 1 starts at 15. So characters 15 will appear in both. That's exactly 5 characters of overlap. The overlap is something we explicitly copy twice. It's a natural sequence of the step between smaller than the chunk size, elegant, relative. Yeah, so we just not copy um, the overlap number of bytes to each chunk, but we just adjust the chunk start to the previous chunk's chunk size minus overlap, if that makes sense. Yes, that makes sense. Ready to move to the next file. Next piece is embed.h and embed.c, the embedding wrapper around GTPUC. It will be simpler than chunk in size. Most of the work is already done with GT embed. Before touching, yes, we'll walk through the logic first. What is even an embedding? So what is an embedding? A word, sentence, or chunk of text has meaning, but a computer can't understand meaning. It can only work with numbers. An embedding is a way of converting text into a list of numbers. Okay, a vector such that text with similar meanings produce similar vectors. Okay, that makes sense. Okay. For example, I love cards, zip on wall 12. Okay, that's just the series of there's the numbers, just a vector, IJKLM, whatever. And then I love dogs. That's again 384 numbers. Okay, I love guys and others produce vectors that are close to each other. Stock market produces a vector that is far away from both. That is exactly why GD small does. It takes a string and produces 384 numbers that capture its meaning. Why 384? Just the size was trained with. Large models use 768, 1536, even 4096. More dimensions, more expensive, but slower and larger. 384 is a good balance for a small model. How does closeness work? And remember, a GT cosine similar measures the angle between two vectors, square root of 1, square root of 0, identical meaning, completely unrelated. Yeah, okay. Right, right. This concept of embedding makes sense before we talk about embed.c. Okay, let us actually create another this thing, and let's do GTC, and let's do git clone. What's the address of GDBC? Okay, let's clone this thing. Okay, let's clone this. Okay, fine. That's fine. Bottom Arif. Okay, and let's do GTE pure C. What's up? Okay, this is just Python script. I don't care. GT.c. Okay, GT small embedding library implementation. We'll just first go through the header. Okay, let's change the color scheme actually. Let's make it blue. Okay, this is just performative maxing. Okay, GT small embedding library is pure C dependency free library for running GT small text embedding inference. Okay, usage for running GT small text embedding inference. Okay, usage GT CTX. So this is just going through what Antares wrote. This is just 70 lines of code, bro. This is just the header. Okay, this is just the header. But yeah, if you go to gt.c, how many lines is that? 900 lines of code. Makes sense. Okay. Okay, we're back in the header file. Okay. GTCTX. This is just the usage that you have. Yeah, so you download the model and you basically call this public API for GT load, and then you pass it into CTX, which seems to be a context CTX handler. Okay, and then float embedding. GT embed CTX your text here. Okay, that's cool. Embedding is a 384 dimensional vector used for similarity search, etc. Embedding GT free CTX. Okay, if this is just the header. Yeah, I mean header foreground. Okay, and then we have include standard def.h. Okay, if def cp c++ extends c, and if if defined, if c++ is defined, extends c. Okay, extends c is not defined. So what does this mean actually? Let's ask Claude again. I believe I missed Mexican Claude. I don't have Claude subscriptions also. Okay, we'll have a reset at 4:30. Okay, okay, Claude. What's up, Claude? Let's use Haiku. Okay. Why? Well, I mean, what does mean? Extend C. I understand extend is the external linking, and which means it is defined elsewhere, and you're just using it. Yeah. This is the standard C++ compatibly pattern for header files. Here's what's happening. See if defines C++ checks if the code is being compiled with C++ compiler. Okay, that makes obviously sense. If it is C++, that this tells the compiler to use C calling convention and linkage for the following declarations. No C++ name mangling. And if okay, so if it is C++, the question part of which would be this. All right. Why? C had a file to be saved included and using but C and C++. Mm-hmm. Okay. Apply C linkage rules to the declarations inside, making them compatible with C function signature. Without this, C++ would apply name mangling to function symbols, making them incompatible with C other files. What is name mangling? I don't know what is name mangling. This is May 11th. Today's. Yo. It's May 11th. Done with Claude. Name mangling C++ encodes function names to support overloading and namespaces at the binary level. Encodes function names to support overloading and namespaces at the binary level. Okay. Oh, okay. Yeah, okay, that's name mangling. Okay. Oh, okay. Oh, okay. Mm-hmm. Nice. Nice. That makes amazing sense. Okay. Opaque context type def struct gt ctx gt ctx type def. Okay. Load model from gt model file, returns null and error. Okay, this is the first public API that we're gonna use. So it is returning a gt context pointer to a gt context struct, and gt load, and you're taking in const model path. Okay, three models and all associated resources gt free, and you're just taking the context and you're just freeing it. That is cool. Generate an embedding for the single text, returns a newly allocated array floats. Okay, generate an embedding for a single text. Okay, that's cool. It generates newly allocated array of floats. Okay, newly allocated, so you're probably using malloc. And caller must free the return pointer, so it's the caller jobs to free it. So we're not providing any helper function to do that, and returns none and error. So float gt embed. So gt embed is a gt ctx pointer to ctx and const char pointer to text. Okay, that's cool. Generate embeddings for okay, that's amazing. I mean, it returns a pointer to a float. So okay, it returns probably, yeah. So it just returns an array to floats, and size is equal to gt dim. So gt dim is the size, embedding size. Okay, cool. That makes sense. Okay, that makes sense. Generate. Okay, we can move on to this. So generate embeddings for multiple text, return newly allocated array floats size equal to count into. Okay, generate embedding. So this is just embedding for a single text, and this is for batch. This is for multiple text. Okay, returns a newly allocated array of floats size equal to count into GTDM. Embeddings are stored contiguously m0, m1, m2, m3. Column is free, the return pointer returns null and error. Okay, embeddings are stored contiguously m0, m1, m2. Okay, that's cool. That makes sense. What is my. Okay, 1 second. Okay, streaming. Okay, we're streaming. And we're streaming, right? I mean, just checking if the stream is working correct. Okay, cool. I mean, it is working fine. How much time has passed? 1 hour has passed. We've done nothing. We just wrote C file, but okay. Now we're gonna do multiple text float gt embed batch gt ctx ctx. So we're just taking the context of the gt ctx. Okay, that's fine. And then we're taking an array of pointer to strings and also the count. Okay. Okay. So it's just an extension for this. Probably you can just call gt embed in gt embed batch, count number of times, taking each pointer to text. Yes, okay, that makes sense. Get the dimension, get the. Okay, that's cool. Get the maximum sequence length 512 for gt small. Okay, sequence length. What is sequence length though? Complete cosine similarity between two embeddings. Both embeddings must have the same dimension. Okay, this is the most interesting that we have for our use case. This is taking const float pointer A, float pointer B. So it's just taking the embedded the vectors, the float pointed to the embedding 1, pointed to the embedding 2, and in dem. So dem is required. Is that right? Why is dem required though? That's the size of the float, right? That's the size of the embedding. Okay, that makes sense. And then we're returning the similarity. Probably just doing a cosine similarity. So probably just doing a dot product. And okay, that makes sense. Okay, we are closing the C++ compiler flag here and end fgth. Cool. Now we're gonna do. Okay, we can see the make file also. Just detects OS for BLAS linking. What is BLAS though? Oh, detect OS for BLAS linking. I don't know. Okay. BLAS linking, as we saw, it is just used for the if you're on a Mac, you can just accelerate the compilation, which I don't fully understand, but okay. All at echo usage make generic pure C, no dependencies. Okay, at echo make BLAS accelerated faster. Generic pure C build generic is equal to C flags plus I don't know what this means though at all. So if you just do make command, it will just echo usage make generic pure C, no dependencies, make BLAS accelerated faster. And BLAS C flags is deaccelerate new LAPAC. BLAS LD flags is framework accelerate. I mean, Okay, that makes sense. I don't know what that means. I think blast is just the accelerator build. Yes. We don't need to care about this too much. What else is there? That's the license. You can read the readme. We can just read the readme actually. Let's just read the readme. Um, here. Okay. So this is the readme. Okay. Dependency-free C implementation small text embedding model generates 3D four-dimensional embeddings for semantic similarity search and clustering. Science analysis of C. No dependencies matches Python speed and accuracy. Disclaimer: this implement was implemented using Cloud Core and tested against the Python implementation. The output vectors are matching, but no accurate testing was performed to make sure the tokenizer and the inference works well in all the cases. If you plan using this library, make sure to verify the results are accurate. Okay, we're planning to use this library, sure, but what do you mean by tokenizer and inference? No idea. Okay, quick start just to make convert model. And I have cards, I have dogs, the stochastic close, cosine similarity matrix, CAPI, load model. Just do this, that's all. And you can just use this things load model and then generate the embedding and compare text. Just do the cosine similarity. That is amazing. That is amazing. And then you just free it after you do that. That's just amazing. That's just amazing. And this is the helper model for just freeing the model and resources. Amazing. Amazing. Amazing performance. Count how many times I said amazing chat. Oh, okay. I also saw Charan in the chat. Hi, Charan. I am just an intern, bro. No, there's a. I don't know. No referral. No referral as of now. I'm just an intern. Performance. Inference time 12 millisecond per sentence. Model load time 20 milliseconds. To model size is 127 MB. That's just the GT embedding model size. So 127 MB. Memory size is 130 MB. Model plus 2 MB. Working accuracy adding to PyTorch or PyTorch. Model load time 20 milliseconds to 12 milliseconds per second. Benchmark Aquil 3. Okay. Was PyTorch. This implements and its transformers PyTorch inference speed within 15%. So this C 12 millisecond. Wow. 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 Okay, that's amazing. Model format GD model format is a simple binary concatenation. Header is just magic plus config. What's magic, dog? Okay, this is a format. Okay, model format. Header magic plus config. Vocab size, hidden dim layers. Okay, vocabulary length prefix UTF 8 strings weights raw float 32 arrays in fixed order. CLI usage. With options model path is path to GT model file. Help is this. Touch GT hello world. Okay, that's cool. Where tokenization where piece tokenizer split text into subwords. Okay, okay, that's the tokenizer. Okay, embedding is token plus position plus segment embeddings. Okay, transform 12-bit layers self attention plus FFN. We don't know what that means. Pooling mean of token embeddings normalized L2 normalized of cosine similarity. Okay, none of that makes sense. So let's see the C code. So it's about 900 lines of code. CD small embedding level implementation, POC implementation of BERT, paste text embedding model. No external. What is BERT? We can actually query what BERT is. So BERT, what's it called? BERT paste text embedding model. BERT-based text embedding model specialized in natural language processing tools derived from the bidirectional encoder representation from transformers architecture. Unlike generative models like GPT, BERT is an encoder-only model designed to understand context by analyzing text bidirectionality, producing high-quality dense numerical vectors, embeddings that represent semantic meaning. Okay. QBERT based embedding models. Sentence BERT, a modification of pre-trained BERT networks using CMES networks to derive semantically meaningful sentence embeddings, making them suitable for semantic search and clustering. Modern BERT embed, okay, maybe it's just the encoder only model, and bidirectional encoder representation from transformers. So it is converting into high quality dense numerical vectors, which is embeddings that represent semantic meaning. We did not take a machine learning course, so we do not know. But general purpose text embedding models like GT, modern BERT base use multi-stage contrastive learning on diverse data to achieve high performance and MDB benchmarks. Key characteristics: contextual understanding. BERT considers the full context of a word based on surrounding words, unlike other static methods like word to vec. Okay, makes sense. Semantic search and retrieval. Probably we can break down BERT in some other stream, but right now I don't think I have the time to do this. As bidirectional transformer built in on unlabeled text to predict mask tokens sentence and to predict this thing. So just from transformers you just implement pipeline is put it as, and there's a Google BERT model there, and it will just produce the config file. Okay, this is the config and parameters, configuration, model, BERT tokenizer. Okay, get special tokens mask, bit tokenize a legacy. Okay, these are all just transformers we do not know ABCD of transformers, so some other time, Charan, I'm watching you, we have to do this. Yeah, we have to do that, bro. Okay, now yeah, let's just see what he has written. Okay, include gt.h, include stdio lib string math c type. Okay, you have to find use class, then all of these compile flags, and you have to include accelerate.h. Okay, probably it's just it is used for Apple Silicon only, I guess, or else if that's not required, use C++, which I do not know what does that mean. Constants, hashtag, okay, sorry, hashtag define GT magic GT1 GTE layer norm EPS 1E. Okay, GT magic is GT1. What the hell is GT magic? GT layer norm EPS. Okay, special token IDs, token PADs 0, uncamp CLS, SAMP mask, hash table size for vocabulary. Okay. Hash table. So data structures. Let's go. Def struct curve pointer word, a string of word. ID vocabulary, that makes sense. Just the hash table, just the key and value. That makes sense. Single transformer layer weights, type def struct self attention. Single transformer layer weights. Okay. Float query weight, float query bias, float key weight, float key bias, float value weight, float value bias, float output weight, float attention, output bias, float attention ln weight, float attention ln bias, feed forward network, feed what does all of this? Self attention, fast forward network. What does any of this mean, bro? Main model context. So this is the config, as he said. The hell. Embeddings. Main model context. So it's like GTCTX. What the hell? I mean, it's defining all of these things. Vocab size, hidden size, num layers, num headings, heads, intermediate size, max sequence length, dim vocabulary, okay, vocab entry, vocab hash. Okay, this is the hash table for word id lookup. Okay, that's the key. And in value, vocab entry, vocabularies, vocab pointer, vocab array, vocabulary words, vocab entry, pointer, vocab hash. Okay, that makes sense. Vocab hash is just the struct here. Okay, embeddings, float pointer, token embeddings, float, vocab size, hidden size, position embeddings, token type embeddings, embed in, weight embed, bias, transformer layers, layer weights, pointer layers, pooler, not used for embeddings but loaded, working memory for inference, utility functions, fnv1a hash for strings. Okay, so this is some bit manipulation that we're doing, just hashing it. Okay, fnv1a, I don't know what that means, but function signature is static. Okay, unsigned, int here returning. Okay, and hash string, const char pointer string, and unsigned int hash. You're doing 21661362661u. So whatever that number is in unsigned int. Okay, unsigned int again is positive, right? While string hash this thing unsigned char pointer string plus plus. Okay, we're taking each character of the string and you're doing an OR between the hash number and the character in unsigned char. Okay, that's interesting. And then again, multiplying hash into that number again. This is an algorithm probably. Non-cryptographic hash function. Yeah. You're updating hash between the um, for each byte to a hash do hash is equal to hash into fmv prime. Okay, yeah. Mm, you're doing XOR between that. Okay, fine, whatever. Like, this is the one A. Okay, fine, whatever. It's just the hash algorithm we're using. Fine. No, don't worry about it. It's fine. But yeah, basically, if you do the hash for the string and then you basically put it as an ID, right? That makes sense. Yeah, add word to vocabulary hash table. Yes. Yeah. So, uh, where's ID? H okay. Table is vocabulary table. Okay. Turn into dot word. Oh damn. Okay. It's not even null. And string copy. Okay. H is equal to h plus one. For that, and then they match id is equal to where the fuck is the id? Okay, because the id they match not word stay or duplicate. They're already doing it here, right? String compare. Okay. Already exists, and then let's just go to h plus one again. Why are you doing that? No edu, no you already exists. So if it's not, it doesn't exist, so just go to h plus one. Oh, okay. H plus one if it does not exist, if it's not null. Um, okay. Already exists. The same word exists. Then return. But yeah, it already exists, and then that's why you put it into the next hash um entry. That's why you do plus one. If it is already, if I mean this thing fails, which means the word is already existing. I mean word does not exist. You just put it into the h entry. That makes sense. And I it up. That makes sense. And table h dot id is what id. That makes sense. Look up word in vocabulary returns minus one if not found. look up word in vocabulary. Static int vocab lookup, vocab entry pointer table, const char pointer word, unsigned int h string. Okay, again lookup word so we were looking up. Okay. Then return minus one. So what are you returning actually? You're returning the ID, right? Yeah, where h is equal to that. It's not null. String compare the word return table h dot id. That's okay. If you have not found it, return minus one. And h is equal to h plus one. Again, why are you doing this again? Why are you doing that? If it does not exist, right? So if the word is different, then h is equal to h plus one, and then keep on doing that until the while loop exits. Okay, cool. Okay, that's okay. I'm so dumb, bro. H equal to h plus one. Obviously, you have to do because it's in the while loop. So okay, that makes sense. That makes sense. Okay. No, I think h is equal to h plus one here does have a different purpose because you're directly doing a table of h. Table of h no word it's not equal to null. Already exists, return. If it does not exist, that's equal to h plus one, keep it there, but also keep it there. Yeah, that makes a different purpose there. Okay, matrix operations. So maintaining a hash table for the word and the id, and your id you're basically doing a hash function. The hash function that you're using is fnv1a. Okay, makes sense. Matrix operation, matrix vector multiplication by y is equal to x at w power p plus p. X is equal to sequence limit in dim w out dim in dim b is equal to out dim. I do not know what this means. Okay, we will see about use plus later, but the layer normalization, G2 activation, proximate softmax over last dimension, L2 normalize in place, tokenizer. Tokenizer might be probably interesting here. Check if character is punctuation for basic tokenization. Okay, if character is punctuation, static int is punctuation, unsigned char c. Okay, return c is greater than, if the c is greater than 33 or c is greater than less than 47 or c is greater than 58, then obviously it is a small number, right? So I mean small letter. Yes, so 45, yeah, exactly. It's like 45 is small a, right? What is small a? Yeah, 97. Okay. Okay, if it is okay, this is just the is punctuation. If it is punctuated, okay, cool. Check if characters white space, basic thing, cool. Basic tokenization split on white space and punctuation locus. Basic tokenize const char put input a char pointer to a string and number of tokens. Okay. Basic tokenization. I think that's what we did, right? Capacity is equal to 64. Tokens is equal to malloc. Capacity into size of class calls done. Basically, what we did, const char pointer p is equal to text. While p does not run out, then skip white space is white space, skip white space, find end of token. Start is equal to p is punctuation, single punctuation is a token. Oh, else read until white space of punctuation. Oh, okay, that's the tokenization algorithm. That's nice. And the create token is just lowercase. Uh, Length is equal to p minus dot. Create token length is equal to p minus dot. How much time has passed? 1 hour 36 minutes. Okay. Create token lowercase length is equal to p minus dot. Car pointer token is equal to malloc length plus 1. Okay. You null terminate it. To lower Startify. What is that? Okay. What is start actually? Oh, start is the P text. Okay, 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 okay. Okay, okay. Oh, okay. Oh, okay, that makes sense. That makes sense. That makes sense. End of token. End of the previous token, and then P minus that. And P is again text. Text minus dot. Uh, um, P plus plus. Okay. Cool. Find the end of the token is actually this the P minus start. Start is the start of the token, and P you just increasing it until you find the um, end of the token. Cool. Yeah, 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 yeah. To list. Yeah, like tokens capacity into cool, 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 cool. The size of capacity is nice. Capacity if you have ran out of capacity, Nice. Again, capacity is 64. That makes sense. Capacity is 64. Num tokens is going to count return tokens. True. Word piece tokenization single word. So you're saying let's see just the tokenization. So tokenization algorithm is just finding the white space, split on white space, punctuation, and lowercase. Makes sense. Makes sense. Word piece token single word. Word piece tokenize. GTE CTX CTX conchar word. Word piece tokenize. You take all of this, and is equal to single length. Word length is equal to 0. Num subtokens is equal to 0. Buffer over subtokens. And this is the transform with forward bus. Self attention. So how do you even write this thing? Insane respect I have like to write all these things. Yeah, this is the dot product between the vectors. Yeah, makes sense. Makes sense. Makes sense. Simple math. This is Okay, that was long. That was actually long, bro. We can use I don't know if I have Claude left. Probably we have to install cursor, but cursor is just the editor, right? So we need the model too. I don't have the model anyway. You'll get back actually. Let's take a small break and a small break of 10 minutes, and we'll get back. We'll get back again.